So we just talked about finding the distance between a point and a plane. Let's use this in a context where it's useful but maybe a little non-obvious at first. Right? And let's do it also to finish something we started earlier. Right? We talked about two planes. They can either be parallel or they can intersect. We did an example already talking about how to find all the relevant information in the case that they intersect. You know, the angle of intersection and the line of intersection. Well, if the two planes are parallel, then the only thing we can really say between them is, you know, what is the distance from one plane to the next? In particular, what is the shortest distance between the two planes? All right? So how can we use what we just derived in terms of finding the distance from a plane to a point in order to solve this problem of finding the distance between these two parallel planes? All right? Well, let's think about first, real quick, why are these two planes parallel? Well, if you look at the coefficients of x, y, and z in both of them, you'll notice they're exactly the same. So that's sort of, you know, the simplest way it can be presented to show you that the planes are parallel. So we're not going to bother actually checking this time that the planes are parallel. Right? Instead, we'll worry about how to actually find the distance between them. So we know how to find the distance between the point, or a plane and a point. Let's figure out how we can do it, how we can use that to solve this problem. Well, think about this. We have two planes, one here and another one parallel, is sort of stuck underneath. Oops. Keep that one solid. Right. So we have these two planes, and what we can really do is just take some point on this top plane, call it P, and then find the distance from that point to this plane down here. And now we're just right back to where we were in what the derivation we just did, finding the distance between a point and a plane. So, well, what do we need then? We need a point on the bottom plane as well, and then we need the normal vector. Well, the normal vector, of course, is really easy to get. The normal vector is just the coefficients of either one of these planes, and since they're the same, you know, it's just 1 minus 4, 2. Doesn't matter which one we read it off of in this case. Okay? All right, so now we need to find the equation of a point on each of the two planes. So the important thing this time is we're not trying to find whether these intersect. We know they don't. So basically now we're trying to solve a system of one equation with 3 variables. What that means is we can pick 2 of the variables to be whatever we want. So again, let's start giving these planes numbers. Say this is 1 and 2 here. All right, so a point on plane 1, well, what we can do is take x and y to both be 0. If we do that, something really neat happens. This is gone. This is gone. We're just left with 2z equals 0. But then, well, if 2z is 0, then z is just 0. So that means the point we get, so this implies z is 0. So the point is just, well, the origin, 0, 0, 0. All right, now we need a point on plane 2. It's a point on plane 2. So here's where we can get a little clever with our choices. Right? So look here, we have just a 1 in front of the x, but in front of the y we have a minus 4, and in front of the z we have a 2. So in this case, it'll actually be a little easier on us if we take y and z to be 0 this time instead of x, right? Because right away, what do we see? Well, if we plug in y equals 0, this is gone. If we plug in z equals 0, this is gone. And all we're left with is x equals minus 1. So a point on plane 2, then, is minus 1, 0, 0. Right? So according to our formula before, we need to choose one of these to be P and the other to be Q. And it really doesn't matter which one. So let's say this one is P, and this one is Q. It really doesn't matter which ones we choose, which is nice. All right, so you might remember then, hopefully you do, that the distance between the plane, whichever one we choose, and the point that's on the other plane is given by d equals the absolute value of the component of n, or the component of QP in the direction of n, right? Which is just, let's write it here, n dot QP, absolute value, divided by the magnitude of n. Okay? So now we just have to write out what all this stuff is. Before we actually do this computation, let me point out a common misconception that I've seen in my many, many times teaching this class. It's very common that since these two equations have the same beginning, x minus 4y plus 2z, it's very common and not unreasonable to think that, well, the distance between them is just the distance between 0 and 1. So the distance between these planes should be 1. That's not going to quite be true here. And let's do the computation and see that. Right? So let's do our computation. N is 1 minus 4, 2. Right? QP, remember, that's tip minus tail. So maybe it would have been a little wise to choose this one to be Q and this one to be P, but it's all good because the minus is going to go away now. So tip minus tail, here's the tip, here's the tail. So we're going to get 0 minus negative 1. So 1. 0 minus 0 is 0, and 0 minus 0 is 0. So that takes care of the J and K components and our absolute value. All right, and now we divide by the magnitude of the normal vector here. So 1 plus 16 plus 4. And square root that. All right, so what is the dot product up here? The absolute value of 1 times 1 plus negative 4 times 0 plus 2 times 0 divided by the square root of 21. Well, what that means, when we actually write out what this is, that just means that the distance is 1 over square root 21. So we can see here, the planes aren't really one unit of distance away from each other. They're 1 over square root 21 units of distance. Okay? But this solves our problem here. We found the distance between the two planes by starting by replacing one of the planes with just a point on the plane, and then doing what we just had derived before, the distance between a plane and a point. All right, that's the end of this marathon section on lines and planes.